Hi everybody, Matt here and welcome to the second video on Let's Code a Networking Stack. In this video we're going to actually write the packet object that we introduced before. So we're going to use a kernel that already exists called X1. It's a kernel that doesn't yet have a networking stack, which is what we're going to be creating. It's written by Richard Braun and it serves as a kind of an educational, bare bones, very simple kernel, which is exactly what we want. A networking stack needs certain features of an operating system, especially things like atomics and things like that. So, we're going to leverage that so that we don't have to worry about implementing those things that we can already assume are there. So let's dive in. So in the source directory, we're going to create a new folder called net. And in here, we're going to create a new file called packet.h, which is going to be our header. So we'll do hash pragma once, and what I will also do is, I'll center this for you. So first thing that we're going to need is we'll look at the transmit side. So if you remember, on the last video, we talked about how a packet will have a series of headers that it kind of keeps references to. So we'll do that by implementing an array of structures, and each structure will then point to one of these headers. So let's do that. So we're going to need a struct, and it's going to have a void start data, which is the buffer that it points to. Okay, and we'll call that headers. And the number, let's call this number of packets headers. So what we will say here is need to hash define number of packet headers, and let's say 8 for now. I don't think we'll need more than 8. Okay, so that's that basic structure done. Now what we're also going to need, we're going to need to keep track of which members of this array have been populated and which haven't, i.e. we need a pointer to the next empty slot in the headers array. So we'll put that inside a struct, and we will say we will call this, let's call it header pointer. Brilliant. And let's just put that back there. Brilliant. So we have our header pointer and we have our headers. Fantastic. Now the next thing that we're also going to need is, well, we will call this the tx struct. So let's call this all of this. Oh, I'm sorry. Let's call all of this tx. This is what represents the transmit side. It's as easy as that. Now let's have a look at the receive side. So again, from the last video, if you remember, the idea is that we have a pointer that's set to we're passed in a buffer, which is the data that's been received off the network. We then set a member called cur_data that points to the beginning of that buffer, and we increment that as it goes up the different protocols in the stack. So let's have that. And we will also keep track of data. Data is always going to point to the beginning of the buffer, purely so that we can free it later on. Let's call this data size, and also let's call this cur_data size. And that is the receive path. Okay, so we can actually put this inside of a union. Because each packet will only either be transmit or receive, it's never going to be both at the same time. So we can put this inside of a union, which really helps things. And let's do that. Okay, great. Now the other thing that we're also going to need is a way to keep track of which direction this is. So i.e. do we access the tx or the rx members? So we'll have that by having an enum, and we'll say tx rx, and we'll call that enum direction. And what we'll also need then is to put that finally in a struct. We'll call that packet_t, and that is pretty much it. Yeah, that's pretty much it really. Okay, so that is our basic data structure. That's how we basically keep track of the packets in the system. What we'll look at now is defining the API that allows you to work with this structure. Ideally, the user or the protocol shouldn't be accessing these members, so they'll do it via an API, which we'll define now. So let's go down here, and first thing that we're going to need is the ability to create some of these structures. So, and so for the receive case, we're going to have a frame and a frame size. Those two things are what have been received by the hardware. And for the transmit case, sorry, I need to create, and that's going to be void. So that just gets you a blank packet structure that just has the direction set. So we're also going to need, so this is where on the transmit path each protocol can push their headers. Oops, sorry. And okay, and finally we'll need a way to free one of these. Okay, right, brilliant. So that's our basic header and our API. Let's now implement the API and write the code that backs this. Okay, so let's now center that. Let's split this, and now let's create packet.c. This is obviously going to need packet.h, and let's zoom in a bit. Okay, so our first function that we're going to create is the ability to allocate one of these structures. So so this is essentially going to do struct packet ret, and then we're going to do, if we couldn't allocate ret, then return null. Otherwise, let's just okay, so that's our basic allocation function. Next thing that we want to implement is the rx create. So struct packet_t rx create, and again we pass in the frame, and okay, so for this we have the ret, and if we couldn't do ret, then return null. Otherwise, the idea with in terms of memory management, each packet will own all of the buffers that it creates. So there's no worry about sharing of buffers and can I free this because it's owned by something else. It's not necessarily the most efficient implementation, but it's the simplest. So what we'll do, rx.data is equal to ret, rx.curData, which is equal to malloc, frame length, frame size, I'm sorry. Okay, again, if we couldn't do that, then we need to say, well, we need to free ret because we don't want a double free. Return null as well. Okay, so now that's done. Let's copy that data in from frame, and it is frame size bytes. Okay, and next thing that we need to do is set the lengths as well. CurData size. I'm sorry, I called this size, didn't I? Is equal to frame size, and let's set the direction as well. Ret is equal to rx and return ret. Brilliant. Okay, so that's the rx create function. Let's do this tx. So this, again, allocate it. And if there's no rets, then return null. Otherwise, set the direction. Easy as that. The next thing that we want is a function that will tell us whether the packet is full on the transmit direction, so i.e. whether the headers array is full. So this is a simple predicate function, so we can make it static because it will only be used inside of this function. So let's call it packet is packet full. Pass a reference to a packet. And what we will say here is return packet tx dot header pointer is equal to number of packet headers minus 1. That's the full case. So that if that's true, packet is full. So now we have that. Let's do the packet push header. Okay, so the first thing we want to do is create a new buffer, and then we want to we want to assume we're making an assertion here that packet dir transmit, i.e. we should be only operating on transmit direction packets. So if is packet full and we pass in the packets, then let's panic. Okay, so that's a critical error if that's the case. We really want to catch that case, and we need to either something's gone wrong or we need to increment the number of headers. I suspect it'll be more likely that something's gone wrong. Okay, new buff is equal to malloc. So we'll let header size. We then, if we couldn't allocate new buff, then enorm, so we couldn't allocate the memory for that. Now let's set tx dot headers at packet tx dot header pointer dot data new buff. Oops, there we go. And in this case, we don't want to set the data, we want to set data size is equal to header size. Okay, take a copy of that guy, thank you very much. And now what we want to do is copy over the data, memcopy to packets tx headers. Well, we can just it's new buff, isn't it? We can just do it to new buff from header size. No, not size off. Sorry, header size bytes. So that actually copies the data. And let's increment the pointer. And I think that's us. Okay, great. So that's the ability now for a protocol to push on a header onto the packet. And finally, last function is packet destroy. Okay. Okay, let's just take a copy of that guy. Now what we need to do is we need to check the direction. So if it's receive, it's dead easy. All we do is we free the RX data. Okay, yeah, easy as that. Otherwise, we will have to now go through each header and free each header. So int I is equal to 0 for I is, sorry, size ti for I is equal to 0, I is less than p tx dot header pointer I plus plus free packet tx dot headers I dot data. So we want to free that data buffer, and I think that's pretty much us. And then the only other thing we want to do is we actually want to free the packet itself, and then finally let's say that. Okay, great stuff. Now what we want to do is see whether this guy compiles. It's probably going to be missing a few headers, but I'm sure we'll get those. And I've also just noticed a typo. Malalok. Yes. Let's see how good we did. Okay, let's add it to the make file. Source net packet.c. Yeah. Ooh, quite a few. Okay, what did I do? Pragma. What else did I do? Size t, unknown name. Okay, size t. What's size t declared in? Is it student h? No, it's not. What about? Okay, good. That got it. String.h. malloc isn't declared. Okay. Stdlib.h. Spool and hash stdbool.h. Okay. Packet. Assert, we need assert.h. Oops. And finally, enolmem. We need erno.h for that guy. And last one, p. Okay, there we go, compiled. So that is our basic packet library. Yeah, so that's, gives us the ability to push headers onto a stack, and eventually the hardware will be using this object to concatenate them and send something out onto the wire. So on the next video, we're going to look at protocols, and we're going to look at creating a small protocol framework to manage different kind of protocols that the stack can sort of handle. and you know, it's going to essentially provide callbacks where these packets are going to be passed around. It's the mechanism by which these packet objects that we're going to create are passed around the networking stack. So that's the next video. Okay, thanks for watching, guys. Bye.